Hello guys, I am Mohammad Reza. I'm sure you just found that on my, channel. This is the very first video. First, I'm showing myself and I'm speaking English. This is not the very first video I spoke English in, but this is the very first video I do both at the same time. This is an and, a logical and there. So, if you don't know me, I'm pretty much a real life Tony Stark. You can see by goatee, but I'm not a billionaire yet. And you can see how I love the character Iron Man by recreating most of his gadgets, like Jarvis. Pretty much that's the only thing have made a part of. Other ones are a bunch of ideas I have written down on my notebook. But if you support me, sorry, I will make other gadgets and I will film them. And of course, I won't limit Jarvis to some 1 or 2 minute videos. I honestly developed machine learning for Jarvis, but people unfortunately didn't support me on Iron Man subreddit. I really expected some support. By the way, if you want to show your support to me, I don't ask for money. I do not really ask for you to pay me in dollars, bitcoins, or any other currencies which are known to humanity. What I ask is just liking this video or other videos if you like, and pretty much subscribing to my account, to my channel. Actually, this is not an account. Of course, this is an account, but YouTube calls that channel because YouTube is some sort of television replacement nowadays. I'm not gonna lie, I really use YouTube as some good replacement for television. I don't watch TV. I really watch YouTube more. I have a lot of good channels on YouTube, which makes me need less of the television. And I'm sure you are like me pretty much. Anyway, if you like this video, subscribe and share with your friends. I will make content like this more and more and more because I love programming. I'm a computer engineer myself. I studied computer hardware engineering. I actually build a lot of stuff, superhero stuff. I like them, and those are fun, and you learn a lot of things. And you learn that it's not impossible to be a real superhero. And everything in between, okay, in between, actually. And if my accent is bad, so forgive me, I'm not a native English speaker. Fine, let's go to this article I have here from vildrevo.com. I will put this link in the description, of course, but let's just read this article and find out how Shazam works. Okay, this is Shazam. This is SoundHound slash Midomi, Chroma Print, and Echo Print. What are these? Imagine you are in your friend's car. Sorry, I make this here. And sorry, I'm checking OBS for once more, and this is okay. This is pretty much okay. Anyway, imagine you are in your friend's car, and your friend has that play system, and you just listen to the music you like in his car. I don't know if I have any music that doesn't get me copyright claimed here or not. I probably should play one of my own songs, the songs I really made. For example, this song, I like the band Polyphia. I'm a rock and roll fan, and you can say by long hair, goatee, or something like that. And And of course, the lockdown after the lockdown in my place because of the COVID-19, I didn't go to barbershop. I'm playing this song for you. Of course, it's not really good to play a song through my phone, through the microphone, but I was so lazy to to just modify OBS to play song from my laptop speakers. Okay? You got the point. You hear something like this, and I do not have a page on Spotify or any other music streaming service. I may consider that, and you can see I'm a musician myself, and I like to find new music. I always love to have new music on my arsenal. So I asked him, and my friend, while driving, looks at me like this. Hey man, I don't know what the hell is this. I like it. And I say, no problem. I open up my Shazam. And he looks at me like, Shazam? You mean the superhero? And I answer, that's better than the superhero. That's the superhero installed on my phone that can recognize every single song I have and I don't know the name of. You know, I have this problem all the time when I am in a cafe, in a friend's car, in a mall, and oh, I almost forgot what a cafe looks like. You know, the last time I was in a cafe was around 4 months ago. By the way, let's not talk different things. And how 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 Shazam can find what is that music. Okay, this article here I'm going to read actually answers that. I know you can just go to wildrevo.com and probably read the article on your own. So I wanted to actually bring my guitar and play something for you while talking about this. But let's not do that, okay? The very first concept we should know is music as a signal. So, what the hell is a signal? A signal, let me see how long I spoke here. Okay, it's only 8 minutes for now, and it's good. Fine. A signal is every function we have, and it has an independent variable of time, like the velocity, like the acceleration, like the angular speed. I don't know if you say that thing. We call that Surat Zawiyi in our language, and we think it's beautiful. And you know, these things are just things that work when we have some changes in time. Let me just go further and talk about velocity. For example, the velocity is the amount of what the hell was that? You know, I know the definition, but I do not know the English words for that. The velocity of an object is the rate of change of its position with respect to a frame of reference and is a function of time. Okay, so you got the point. For example, if my finger is here and it take me 5 seconds to take it here, which I believe took less than 5 seconds, and let's make it a bit more scientific. I start here, which is the most right side of my laptop, and my laptop here has around 35 centimeters. and it takes 5 seconds from this side to this side in the speed I got. And I can say it was 7 centimeters per second, okay? So time didn't change, but the position of my finger changed. Okay, time has its own way of changing and doesn't really depend on my finger. Time passes no matter if I move or not, if I speak or not, you got the point. So every function we have, which is function of time, can be a signal. If you studied electrical engineering or computer hardware engineering or software engineering nowadays, or you are interested in AI, you pretty much have something called signals and systems, which is the basics of digital signal processing, and that is what we are going to do right now. Okay, so we have something which is called the fast Fourier transform. If you are not familiar with transforms, which is really okay, you know why? Because there are tools that can help you understand these things, but we have something here which is pretty much the very same concept of fast Fourier transforms. I'm not even good at mathematics, I may look like a person who's good at mathematics, but to be honest, I'm a person who's good at using a calculator and not more. So here, I just leave reading this article carefully to you, but it was really cool for me to know how Shazam works. So I decided to just make it to a video and talk about that, and we may just do a lot of codings in later videos. Here we have this formula here. This is a really long formula which gives us 16 million samples. Okay. I just make my facts a bit simpler, make my actually talks, and fortunately I have something in my arsenal. Okay, there is a potential security vulnerability in one of your dependencies. Okay, I will I will just fix it later. Here, a while back in another channel I made a Persian course of digital signal processing using Python. And here I'm just going to talk about this sine wave and this sawtooth wave. Let's see this sine wave carefully. And I think I have my tools here. No, I don't have, I believe I had my notebooks here. Okay, this is my notebook. And I'm waiting for the notebook to be loaded. If it's not loaded, it means my connection is not really ruined yet. So the basic formula of creating a sine wave is 2 times pi times frequency times time. And it's actually a sine function of this formula, and using the numpy sine method, I forgot the name, I made this. And afterwards, I actually created this 1 hertz frequency. And after that, I actually created something to just do the harmonics. And the harmonic is actually a multiplier of the frequency, and you just need to divide the whole signal by that number you are multiplying your frequency in. Okay? We are good. So we had this, and adding harmonics to it just transformed. And this is the Fourier transform, if you are not familiar with. And using these transforms, we just made a lot of transforms. And I may just create some videos about how you can make these shapes and even make audio signals out of that, which is really, really, really great, I believe. But Fourier transforms are not really hard to understand, especially if you have the basic understanding of integrals, the basic understanding of differential equations or something like that. And if you don't have, please do not panic. There are a lot of websites, tools, and courses that can help you out with those. So, are we good? We are. Of course, we are. And you know why I was looking for this sampling stuff, but we just looked at a bunch of Python code. I want to put this notebook in descriptions as well. So only God knows how many times I'm going to just review this video to find out what links I'm going to add to the description. Sorry for the language interruption. So we have something. We have this time in seconds, which is really easy to calculate. For a 3-minute piece or song like AC/DC's Back in Black, I think it's about 5 minutes. We just take the whole number and multiply it to 60, and we kept the seconds, we add it to the seconds. And we also have 2 channels, which means we have a multiplier of 2. But what is 44/100? Okay, here we have to go a bit technical. Computers do not really understand analog signals, and if we are storing analog signals like my voice, like your voice, like music, like data of earthquakes, these are analog signals and they are not digital. We have to make them digital signal. If you are familiar with microcontrollers, you will know there is something called ADC, or analog to digital converter, which converts any analog signal from a sensor, from a microphone, from I don't know, everything that can output analog type of thing to the device. And this is the pretty same concept. We want every single detail of our audio signal, like my voice, be as similar as possible to the original signal. Okay, let me just reposition myself. I think I will get much older the time I found where to put this microphone. Or maybe I should get one of those lapel lavalier microphones. Anyway, let's talk about this number. And then we design the sampler devices, like the audio interfaces we have, to devices that can take 44,100 samples of the sound per second. Let's see here. For example, if this is a 1 second of something, which is 1 second, you can easily see every single dot which formed this is just a 100th of a second. And here we just multiply 1 second by 44,100. And this is a very small interval, and it makes the sampling lossless. Lossless means we do not really lose anything of these samples we have. Remember the old times we had 8 bits of audio data frames, I should say data lines, and how they did sound. And now I can easily make an audio signal using this app called Logic Pro sound much better than the original one I recorded in front of this microphone, because this microphone is not really good for recording guitars, but I record my guitars using this microphone as well. So this is the whole thing. We have this type of samples, we have this amount of seconds, and we have 2 channels. That means we have 16 million samples for a song. Isn't it beautiful? It is. But sometimes I personally ignore the whole 2-channel thing and record in mono. And if I need stereo, I really record in a separate channel and pan it to left or pan it to right. And these are studio magic, but at the end we have stereo file exported as the MP3 or WAV files or something you can see. And here we just have the sampling. Okay, actually the sampling wasn't my all-time favorite, and I didn't really learn it very much. You know why? Although this paragraph or this section is really, really cool to learn and read, and I will read this afterwards, but let me tell you one secret. We do not really need these sampling formulas or these sampling methods anymore, because this Nyquist-Shannon sampling theorem is the basics of digital audio workstations like Logic Pro, FL Studio, Audacity, LMMS. There are tons of software you can buy, download, or even write yourself to record music, record instrument, or record your podcast. So here we just have this thing here. I really suggest, if you like this, please go ahead and read that. it's previously written. So how you can write that? Maybe you write a blog on my video. Who knows? Okay. No one can get away from my jokes. And this is my most favorite part of this article is the spectrograms. Formerly I really learned how to make these things using Audacity, but after this video is shot, I have an unfinished course here. I will finish this and I will learn how I can make spectrograms of songs like this. This is really cool, and I'm sure there are tools to make spectrograms of songs. And I also saw some people, for example, put a photo and make it to some noise, and then when you get the spectrogram using Audacity or any other software, you can see this is a photo. And the most famous one was a mysterious video you can find in my channel. I kinda decoded it, but it was pretty much wrong. I really wanted to put a prank on my friends. But that video was a plague doctor, and it was filmed in 2015. And anyway, let's conspiracy theory be somewhere else. So as you can see, it's just a 2D array with amplitude as a function of time and frequency. The FFT shows us the strength, amplitude of the signal at particular frequency. This is great. Giving us a column if we do this enough times with our sliding window of FFT, we put them together to get a 2D array spectrogram. These spikes are actually the times we have the lowest points in the sine. And this is why I'm really pissed off by this loudness war we have in modern day music. First of all, have you ever thought of your ears when you mixed and mastered songs like that? And second, please mind there are a lot of programmers going to make their own version of Shazam, and they probably need to have less picks. Of course, having more picks is more making our final model more accurate, but for now, I just wanted to make some jokes. So as you can see, red means the higher. The color shows the real value. Amplitudes here are real valued. So when we have red or orange, it means we have load spots. So I don't know the song, but if it was my song, I think it must be the times I hit the crash symbol on a drum kit. But if it's a Justin Bieber song, I think it's every time he says baby. Or if it's a Billie Eilish song, I don't think that has so many picks, She whispers at the microphone. Okay. Really can't get away with my jokes. Anyway, we have a peak finding. So we define a peak as a time frequency pair corresponding to an amplitude value which is the greatest in a local neighborhood around. Other time frequency pairs around it are lower in amplitude and thus less likely to survive noise. Which is true. Let me just drink a bit of my tea. Sorry, my mic just hit the mic, and if you heard something, when you record very low, what does it mean? It means that very low and it can't be heard. It means if someone is yelling in front of you, even you yourself can't hear the note on your instrument. But if you play loud enough, and this is why when you see videos of people who are giving you tips of playing the guitar in a studio, you really find something, in every video that is peak as strong as possible. And this is the same idea. When you pick strong enough, you just don't let the noise get into guitar pickups or microphone. And this is why I'm almost yelling at the microphone. You know why? Because the TV is on in the other room. My parents are watching TV. My mom is preparing the dinner, and the phone may just ring. I don't know, maybe someone just rings our doorbell or something like that, and I don't want that noise to get into my microphone, okay? And let's see. So we just have these coordinations, and everyone which has the more amplitude is our peak. So finding peaks is an entire problem itself. I ended up treating the spectrogram as an image and using the image processing toolkit and techniques from SciPy to find peaks. A combination of a high-pass filter and the SciPy local maxima tracks did the trick. Okay, to my eyes, these are the peaks. And others are not. Once we've extracted these noise-resistant peaks, we have found points of interest in a song that identify it. We are effectively squashing the spectrogram down once we found the peaks. The amplitudes sorry, amplitude is an amp simulator. The amplitudes have served their purpose and they are no longer needed. Let's plot them to see what it looks like. Okay, I was right. All of these are peaks. You'll notice there are a lot of these. Tens of thousands per song, actually. The beauty is that since we've done away with amplitude, we only have two things, time and frequency, which we've conveniently made into discrete integer values. We've binned them essentially. We have a somewhat schizophrenic situation or schizophrenic situation. On one hand, we have a system that will bin peaks from a signal into discrete time frequency pairs, giving us some leeway to survive noise. On the other hand, since we've discretized, we've reduced the information of the peaks from infinite to finite, meaning that peaks found on one song could, will, of course they will, collide, emitting the pairs as peaks extracted from other songs. Different songs can and most likely will emit the same peaks. So what now? Okay, this was really interesting, and I think I have to grab my guitar now, but let me search something for you. Okay, this is not this lick. And here we have it. Sorry guys, I have to leave and find this this is a music joke, okay? And, I'm grabbing my guitar. Yes, I have my guitar. And here we have, okay. Sorry, I ruined that. But the whole concept is, have you heard it? Okay. Okay. So I lower my microphone to my guitar so you will hear this. So let me just make a point out of this lick. I will be back when I put my guitar back there. I will talk to you about something. You know why the lick is so famous? Because the lick has been heard in lots of jazz music. So I consider pretty much every jazz song has the lick inside. So they may collide. And, imagine I have a song by Louis Armstrong and I have a song by Duke Ellington and I have a song by, I don't know, maybe Adam Neely. By the way, he's my favorite YouTuber, by the way. And my software can easily tell me this is a song by Adam Neely while I played the lick part from a song by Duke Ellington. Duke Ellington died way before I was born, so it can't be possible, Anyway, so we need some, this is the point and how we solve these bottlenecks. So we might have similar peaks, no problem. Let's combine peaks into fingerprints. And this is the whole thing, Shazam, SoundHound, and even this really new service from Google does. A hash function takes an integer input and returns another integer as output. The beauty is that a good hash function will not only return the same output integer each time the input is the same, but also that very few different inputs will have the same output. By looking at our spectrogram peaks and combining peak frequencies along with their time difference between them, we can create a hash representing a unique fingerprint for this song. Sorry, I'm really terrible at reading, okay? Hash gets frequencies of peaks, time difference between peaks, and then returns the fingerprint hash value. You know, you can write a hash function. This is not really hard to do. You know, we have 3 peaks here, and we have 3 peaks here, and 1 peak here. And from this peak, we just get these, and you know, this is how the hash function works. And after that, we are going to the database and stuff, and I'm not going to talk about the database and stuff here. Why? Because in a future video, we may try to just rewrite or actually write the whole thing explained in this article. And afterwards, I'm going to, use the library this guy made called Deja Vu. And using Deja Vu, we can make our own Shazam. So guys, I hope you found this really useful. Please do not forget to like and subscribe and share this video with your friends. And until the next time.